today it's all about the filter selection guide for industrial and machine equipment. The idea is that we publish or will publish a document how to select filters according to the needs in industrial and machine equipment. So it's a 28-page document where you can see different criteria how to select the right filter. And today I will try to give a detailed or a little bit detailed overview, let's say, about this guide you can see in this PDF. Good. So the agenda of today, of today's webinar, and the specialized part of this webinar is the EMC standardization and frequency range first. Afterwards, we will go into detail for the standard IEC 61800 adjustable speed electrical power drive systems. We will see how filters are used in industrial equipment and machinery. Afterwards, we will try to, or I will try to present how to distinguish between residential, commercial area and industrial environment. Afterwards, a little bit of a breakout for network configurations. Then we will have a look at the decision help, how this works. This is like a selection tree, which you can start at one entry point, and afterwards you see different details, how you can select your filter afterwards. Then we will have an EMC measurement example on different filters, and at the end I will go a little bit into detail for leakage current in complex systems. Let's say a leakage current measurements. So this is a really hands-on seminar at the end where you can see real measurements of our filters within a drive system. Good. So as I said, the frequency range and standardization is one point that needs to be known before we start, because Schaffner EMC is focusing on 150 kilohertz to 30 megahertz. This means the conducted emission levels we are talking about today. Some standards, like lighting standards, start a little bit lower at 9 kilohertz to 150 kilohertz. So if a standard needs to be reached there as well, an EMI standard or EMC standard, then we also have filters for this dedicated standards. For example, the new FN 2580 is a lighting filter, which is also relevant for this frequency range. Then even lower, 2.5 kilohertz to 9 kilohertz. This is Schaffner internally called the medium frequency range, where we do supply LCL filters as functional part of the system. LCL filters are a combination of 1L, so one choke, then a capacitor and another choke, which are in front of a regenerative drive system. If a drive system is regenerative and it wants, or it can feed back power to the grid, then the LCL filter is needed at some point that this is possible. So this is why it's a functional part of the system. In general, EMC filters are not so-called functional part of the systems, but they are parts of the system to be consistent with the standards you see later on. One step lower in frequency, we as a Schaffner group are able to cover so-called harmonics. The harmonics are harmonics of 50 hertz or 60 hertz, which is the grid frequency. And this is covered by our power quality products. So this is all about the frequency range. Now we are going a bit more into detail on the power drive system, the so-called PDS. On the right side, you see a picture how the PDS is seen in terms of the standard. So IEC 61800 defines the power drive system as a modular system built out of the PDS power drive system, the CDM complete drive module, and the BDM, the basic drive module. And the filter is part of the CDM. So the complete drive module or the power drive system incorporates the filter inside. If we are looking at those blocks, you see different conversion stages on the right side. So if you really look on the right side, I will just use my pen. Just 1 second, please. So if you look here we have the grid coming in. And then we have the EMI filter. We have the AC-DC conversion from grid AC to DC, the DC link in between, which is this one. Then we convert back from DC to AC. And at the far end, we are supplying energy in a different frequency to the motor. In general, EMI problems occur when we have this AC-DC and DC-AC conversion, because we have one frequency of 50-60 Hertz coming in, and then we need to adapt to a motor switching frequency which is higher, usually around 4 kilohertz or even higher. With new approaches like new SiC or GaN semiconductors, it's even higher than 15 kilohertz or around 100 kilohertz. So it's really high frequency, and this switching frequency conversion causes losses, which should be clear to all of us. And this is why we need EMI filters if we are connecting to the grid, if we want to connect to the grid. Okay, having said this, we are going more into detail where in this complete drive module our filters are used. EMI filters are used in different areas, directly at the drive or as a sum filter. The sum filter will be also explained on the next slide, but you can already take into consideration that the sum filter is used as one filter at the grid entry point of the machine. So you only have one, not directly assembled to the drives in a distributed drive systems. If you have more drives than one, it's just at the entry point of the whole machine. Or at the logic, you could also have EMI filters to prevent the spread of interference from the control unit and systems interference into the control unit. Just need to. And what's displayed here as well is the output choke, which increases the longevity of the motor. So example, if you assemble one reactor in between in the output, then it might reduce ripple on the bearings, so the bearings might last longer. But this is not in discussion for today's selection guide. Good. So here you see 3- and 4-wire filters, which are used in general as a sum filter at the input of the machine towards the mains, or for distributed system used directly on the inverter to suppress the spread in the system. This is what I meant before. So we have one filter at the entry point, or you have distributed filters all around. For smaller power ratings, also single phase filters might be applicable. So we also have some EMI filters for single phase motor drive system in our standard portfolio, and a customer base as well. So customer specific products are also single phase products. The general rule for filtering is that the filter should be as close as possible to the source of noise. Sometimes this is not possible due to various reasons, as written here, for space reasons, for example. So if you don't have the room in your system, then you might want to have only one as a sum filter. Or costs. If you don't want to have, let's say, if you have a 12-axis machinery, then you need 12 filters, or you need one. So maybe the one filter is more, so the one filter will be more expensive than one of the 12 distributed ones, but it might be possible that one sum filter is less expensive than 12 others. Okay, single phase filters at the control unit are used in complex system for filtering of noise from the control equipment, so the emission of the control equipment itself, or protection against EMI noise from surrounding systems, the immunity. And they are increasing the reliability of the whole system. This is the idea for single phase filters. You see here on the left, one with really special terminals. So the FN2415 has this terminal types for machine builders, for example, that they are touch safe. The FN2060, you see here, they have this fast on. If you use isolated fast on connectors, then this is also possible to be connected in an easy way. There are also cable versions available for this one. So now you saw how we position or how we select filters according to their use in the power line or in the signaling line or control unit lines. Now we are trying to distinguish where these filters are used. Are they used in the first environment or the second environment? Because this is very important for selecting the right limits you need to reach for your application. So when you select filters, it's not only the position in the system important, the position of the system in the grid is crucial for the selected limits. We differentiate between the first environment, as I said, which is the residential, business, and commercial area, also known as public low voltage network, where you have low limits for emission, but also low limits for immunity. So if you disturb others not in a high way, then the other one don't have to be so immune against the disturbances in the system. For industry, it's a little bit different because we have very powerful machines. So we have a dedicated medium voltage transformer, and we have these powerful machines which are causing noise. So they are very noisy, so you need to be very immune, or you have to have high limits for immunity as well. If we are looking here on this slide, just 1 second. Looking at this power network specification here in this on this slide, the TT and TN power network, or TT, TN, and IT power network for industrial. We need to I try to explain it a little bit or show you what this is about. So there are different kinds of networks all over the world used in different contexts. So this is, as I said, only a small breakout. I just want to show you which kind of different configurations for grid networks we have around the world. And that I just want to let you know that we have different kinds of filters for this kind of network configurations. The IT, the insulated transformer, for example, we have the IT grid network filters, which have a little bit different setup of the resistors. The discharge resistors to Y, to protective earth, need to be a little bit higher than others, because without this one, we are not able to do insulation measurement in this IT grid network. So they have to be higher than 1 mega ohm. So this is, for example, common in Japan or in different other countries around the world. Good. So just a small breakout. Now we are back in the document, in the selection guide. And according to the selection guide, there are these two environments we already discussed. And then we need to distinguish if, for example, for the first environment, do we have unrestricted availability or do we have restricted availability? If it needs to be available at all time, then we need to reach the emission category C1. If we are in the first environment and you need to, there is no really unrestricted availability, then we can go to level C2. For the second environment, the industrial, we have the C3L, which means low, which is below 100 amp of current, nominal current. And we have the emission category C3H, which stands for high, which has a very high power rating. So you see, going from C1 to C3H, the limits are rising substantially. So in residential surroundings, you might see 40 or 45 dB microvolt as the limit for average measurement. And in the C3H, you have above 100 dB microvolt on the average measurement. So this is a quite high differentiation between both. As I said already, for industry, it's powerful machines, and this powerful machines will even cause more disturbances. So this is why the power level C3H, the category C3H, is available for these limits. if you found out which kind of level or which situation you are in, if you are in industrial, you will see in our document that there is different selection trees afterwards as well. So here, the differentiation between those two is that you start in an industrial environment, but then you have this variable frequency drive not interference suppressed, so there is no filter inside, or if there is already a filter inside for C3, this is the one on the right side. And then you see in the lower tree, you see a distinction between the cable length and the axis, for example, for not so complex system. Let's say for one drive with 30 meters, you can use FN3288, for example, which is the high performance 3-phase filter, or FN3359. If you go more on this complex side, 12 axis, you also see here the FN3288, and I will discuss this later on why it's the same filter here. So you have different variants of this filter, but here also the FN3120, for example, comes into the game, because this is a very high performance filter for these 3-phase applications. And this is how this filter selection guide works. So you just see, you look in which industrial or in which environment you are. Afterwards, you see what's already done in your drive system, and then you can select how your drive system is built. So at the end, you just need to select 3-phase or 3-phase plus N, and then you directly see the filter model you can use. What's important in this selection guide, it gives an indication. So in general, our filters are tested with different drive setups for different cable lengths and with different numbers of drives. But we cannot test everything. So this is why, in general, it should be measured in the application to see if it fits or not to the general limits you want to reach. Okay, same here for the residential environment. So also there you need to distinguish, is there already something in the drive or not? And which kind of category you want to reach, and then cable length and number of axes. And at the end, there's also the filters you can select for those kind of applications. So I think this is straightforward, and if you review the document later on, you will directly understand how it works. Good, so now this is also another small breakout session of the document, which this is not really mentioned in the document, but it is crucial for our filters as well to understand how the naming of our filter is done. So here, for example, the FN3288 is the high performance version of our newest and smallest book style filter we can offer as a standard part. Then this HVIT is a special version. So this means high voltage for IT grids. Then next number is the nominal current, 10 amp. Then we have the terminal type, 44. 44 means this kind of a safety terminal block where you can connect solid wire, flex wire in these diameters, and we also give a recommended torque for the screw. And then we have C26 and R60. The C26 is the Y capacitor key. So if this is higher number, then the Y capacitor is also higher. You can see this on the left side. C26, for example, is 3.6 milliamp for leakage current. And if you can go as a higher leakage current limit, for example, 4.6 milliamp, then you can select the C42. The R60 is also a key for the X and Y discharge resistors. So this means the 6 is the X capacitor discharge resistor, which goes along with the X caps, and the 0 is the Y discharge resistor. So the 0 here means that we have no discharge resistor. So we just have the resistance of the capacitors itself. For older products, we don't have this nomenclature. We are using for the Y capacitors, we are using this kind of letters here. So FN3270H, for example, this Q1 version is a special Y capacitor built in the FN3270. And you also might know this FN2060A, for example, or B. All these letters just directly behind are meaning different kinds of Y capacitors used. Good. So now we are going a little bit more into detail for the real measurement, so EMI measurement of a 10-meter cable with shielding for the FN3287, which is the standard performance version of 3288. So 3288 is the high performance version, 3287 is the standard performance version with high Y caps. So you see, if I start the video here, so the measurement is okay. You are in the lower frequency, you are a little bit low, a little bit close to the limit here, the limit lines, the average and the peak measurement, and everything is okay. But if you compare it to the high performance version, for example, which is the next slide, you will directly see here, this is the comparison of the FN3287. And on the upper slide, you can see the measurement done with the FN3288. So the high performance you can directly see in the low frequency, it's around 10 dB less. And it's far away from the limit. And for the higher frequency, everything is lower than before. So this is the same configuration, just the filter is changed. If we look at a filter, or if we compare different setups, for example, shielded cable or a not shielded cable, or let's say the cable itself is shielded as well in this measurement, but the shield is not connected to the drive anymore. It's only connected to the motor side. You can see here in this measurement, a measurement of 25 meters with shielded cable. So if I start now the video, the golden lines, which you saw before, will move up. And this is a new measurement. So the new measurement is without shielding. So you can directly see the comparison in the frequency range about 1.5 megahertz. Without the shielding, it's going up. And in the higher frequency range, it's quite substantial difference. So the green line and the blue line is the old measurement with shielding, and without shielding, it goes not above the limit, but still quite close to the limit. And what is impressive here, I would say, is the difference between used with shielding or without shielding. Good. That's all for EMI measurement. So the next slides afterwards will be about leakage current in systems. But if you have some drive systems you want to get tested, for example, we invested heavily in a high-powered drive lab, which I mentioned already at the beginning. This is in Switzerland, and we have the ability to test drives up to 500 kilowatt. So on the right side, you can see the drives itself. So this is the room next to the cage on the left side. So the cage on the left side is the measurement part where you can attach drives, for example, and get them tested. We have a transformer in place where we can use different input voltages and simulate different grid voltages. And we have the ability to test more or less every drive setup which is available, going up to 500 kilowatt. If this is not enough, even not enough for you, and you have a special drive which you cannot disassemble on your side, then we are also able to travel to you and take measurements on site. So this is one additional service we can offer. Good. As I said, next point will be leakage current in systems. And one point here is that I want to show you how we are dealing with leakage current on our data sheets. So we had a lot of customers asking, why are the leakage current indications on your data sheet so different to what I see in my application? This is quite simple because or easy to explain, because we are just using a calculation formula for this according to the standard, the IEC 60939-3, which is the filter standard for safety for EMI filters. And this is just based on the grid frequency and the voltages we see in the filter, in the grid. So if we have an application with higher switching frequencies, then it might look completely different. And also cable length, shielding, everything is somehow bundled to the leakage current we see in the complete system. Therefore, the leakage current needs to be measured as well. So it's not only a calculation. The calculation basis we are supplying can be used to distinguish if filter models are different to each other. So if we, for example, have a low leakage current version, the leakage current calculated is lower, and in the application it will also be lower than the usual version, but we cannot really say what the leakage current will look like in the application, because it can be a very complex distributed system with different kinds of filters, different numbers of filters. So the combination makes the system at the end. The circuit breaker or the fault indication circuit breaker always measure the complete system and can be selected according to different trigger currents. So you might have 30 milliamps or 300 milliamps. 30 milliamps is because of safety for humans, and 300 milliamps is because of safety for fire. So there we need to distinguish which kind of installation you have, and then you can select filters accordingly. To show what this looks like at the end, how to select the filter and how a measurement looks like, I have some examples of measurements here. So now you need to look very carefully on the slides, because only the C value changes, or the FN 3288 will change. So for example, if we have a 10 meter with shielding cable with this standard performance filter with the high leakage current version, or with the not usual, let's say usual version, we can see that we have about 35 milliamp of leakage current in the system. If we compare to the next one, which is also, sorry, I mixed up my slides. I will show the comparison between the two filters later on. Now, more general on how we do the measurement for leakage current. So now this is the same filter measured with a real drive system, and you see here the frequency, the different frequencies we can see in the system for leakage current. And this curves gives an indication when the FE might trigger. So here you can see that it does not trigger on the measurement basis you can see here. So this is how we do measurements if FE is triggering or not. This is a quite detailed measurement, and we can see different components of frequencies here. If we just need a qualitative, not really quantitative analysis, our tool also gives the indication, yes, it's green, the light is green, this FE might be used. So here only 6% of this 30 milliamp FE is reached. This means we have still 94% left before it would trigger, and the higher values also are in general higher. So you see 4% reached, 4% reached, everything is green. You can use any security device you want to use in this kind of application. Good. So now going back, I don't know if you still remember, but in this standard performance version with the high leakage current, the C33, I think it was, we saw about 35 milliamp of leakage current. Now we have this C21. C21 is the very low leakage current version of the high performance filter. And here you can see it's only 40 milliamp of leakage current. So in general, the leakage current is more or less half. And this is only done because of the different C capacitors here. If you use a high C, so C21 to C35, same filter, only the C is changed. We also go back to about 35 milliamps. Configuration, the rest of the configuration was the same, so 10 meters with shielded cable. Now we see 25 meters with shielded cable, also C35, so the high leakage version. Here you can see it's a little bit different. So the leakage current is going down. This is not really a problem, but this is connected to the resonances and the length of the cable. So the cable length might help to reduce the leakage current of the whole system. But this is also just a detail and needs to be measured at the end, and it's fluctuating over the time. So this kind of measurements need to be taken very carefully. Now what we see here is the measurement of a cable without shielding. So now it's connected, as I said before, it's only connected to the motor, not to the drive anymore. And you see directly that the leakage current is going up compared to the measurement before. So it's 10 milliamp up. Good. And this is also already my last slide, just to show you what we can do for reduction of leakage current. So there are different possibilities. You already saw this in the measurements. We can exchange the different C values. So if we reduce the capacitors, the overall filter gets less performance, or let's say the common mode performance of the filter is going down. This is why we need to balance this by the quality of the core material or by the performance of the core material. This is why we have this FN3287 and 88. So if we reduce, for example, the C values, then in most of the cases you need to take the FN3288, which is the high performance version. One main advantage of Schaffner is that we already have the different variants of CY in our standard certifications. So if you need a different kind of filter with a different C value, then you can directly select one and you can get it built in a couple of weeks without additional certification based on our standard portfolio, which is the main or a good advantage for our filters. So it's fast track. You can directly select out of a table which ones you need, and then you can get it tested. Additionally, if you have the ability to use a 4-wire filter, then this might reduce your leakage current, not discharge current. This is a little bit of wrong wording. Okay. So 4 wires with the attached neutral will have not as high leakage current as others. One last point, which I would like to point out a little bit more, is that we have the ability to actively reduce the leakage current by measuring fault currents and feeding back in opposite polarity. This is at the moment at the prototype stage, and if you have some kind of application where you think you might need this kind of active reduction, then you should write me an email and we will try to find a way to get it tested, or maybe first discuss if this is applicable for you or not. Good. As a small summary, we saw for today first introduction of Schaffner. I hope you still remember what Schaffner is about. Then we saw the introduction of our new filter selection guide, which you can download as a PDF from this web meeting. And at the end, we shortly discussed leakage current for Schaffner and how it might be possible to reduce leakage currents. Thank you for attending. If you have questions later on, just let me know, as I said already. I would be more than happy if you stay just a small minute afterwards so you can answer the questions on the quality of this webinar. And yeah, I hope to receive some inquiries from you and talk to you soon. Thank you. Goodbye.